In this video, we're going to look at how to generate random variates which are non-uniform, and one very important set of such variates are so-called Gaussian variates. I may wish to obtain values which are randomly selected but which have a probability density function, a probability which is clustered around 0 and has some defined standard deviation. So let's see how we might do that. As usual, I have the MATLAB main window. I've started a new script and I'm going to call this Gaussian Variates. So how might I generate a Gaussian distributed variate? Well, the inbuilt pseudo-random number generator, which, as we have seen in the previous video, is related to but not exactly the same as a linear congruential generator. This pseudo-random number generator, by default, generates numbers which are uniformly distributed between 0 and 1. So if I ask for a value u equals rand, then I will obtain a single number between 0 and 1 with an equal probability anywhere within that range. Now, what would happen if I generated two of those numbers? Well, let's save that script and we'll call this Gaussian example, something like that. And I'm going to run it just to see what we're generating, and we generate on the right hand side two random variates, 0.8 and 0.9, as it happens to be in this particular case. And as usual, I'm going to say close all and clear all so that my script is not interfered with by anything else that might have been run previously. Run it one more time. So I've got two random variates. What might I do with them? Well, I could add them together. Now let's just look back at the help file. The help for the sum function, which I'm going to guess is the correct function to use. The sum function, yes, the sum function sums up the elements of a vector. So u, in this case, is a set of uniformly distributed random numbers. So what I can do is I can sum those numbers together. So I'm going to just sum them by putting a bracket around the outside. And I'm going to change what this is now. I'm going to call this now g. So g is going to be my single value. Okay, so u was an array which had two uniformly distributed random variates, and I'm going to add them together to make a single single random variate. Now, I want to do this procedure many times, so what I'll do is I'm going to generate n samples. I'm going to select maybe 1,000 of them, and I might be able to do this in a more compact way, but just for clarity, I'm going to do this 1,000 times. I'm going to, for each one of those 1,000 times, and I'll just put a tab in there to make it look a bit nicer. So for each one of those 1,000 samples, I'm going to generate two uniformly distributed random numbers. I'm going to add them together, and I'm going to put that result into my value g. So there'll be 1,000 values of g. And I'm now going to histogram that to see what that looks like. So I save it and run it. So I run it and aha, I get something which is no longer uniform. As one might imagine, if I add together two numbers which individually lie between 0 and 1, the result is likely to lie close to 1, more likely than to get values out in the wing. And a good analogy for this is if I roll two dice that can give numbers between 1 and 6, it's unlikely that two sixes will be rolled. It's much more likely to have a combination where the result is closer to the mean value, which in the case of a dice is 3.5, and in the case of these two uniformly distributed random numbers, the average value for each roll, for each uniform number u, is 0.5, and the sum therefore has an average value of 1. So let's extend this. Let's make that number 3 instead of 2. It takes a little bit longer to run, of course, but when we do that, we have something which is beginning to look a little bit more Gaussian. Now notice that the mean value has increased. It's now 1.5. We'll have to fix that later, but for now just look at the shape of that function, shape of that probability density function. So the random variate g has some probability density function, some probability of lying in a certain range. and I've obtained that numerically by taking 1,000 samples and then histogramming them. So I could make that histogram, if I have 1,000 samples, I could make that a little bit finer by having 20 bins instead of 10. See what that looks like. You see there's a little bit more noise, but I get a little bit more detail. This is running quite fast, so maybe I'll do 5,000 samples instead of 1,000 samples. And we'll see how that looks. And you get, again, you see some fluctuation. And as we saw in a previous video, the approximate rule of thumb is that the likely fluctuation of each one of these bin counts is approximately equal to the square root of the number in each of those bins. So if it has an expectation value in the middle of around about 90, we expect to have a variation of about plus or minus 10 or so. Now let's increase this number to, say, 5, and run that again. And now, once we increased how many uniformly distributed random numbers we're adding together, so here we're generating 5 uniform numbers, we're adding them together, and the result is a single variate. And this single variate, once I've added together a sufficient number of these uniform numbers, this value g, is now looking a bit Gaussian. It's looking like a Gaussian variate. It's not quite Gaussian because, of course, if I don't have many of these numbers added together, then it's actually impossible for the numbers to lie out in the wings. So there is a restriction to the validity of this approximation, as it is, in that I can't generate values which lie right out in the wings. This is just the same as if I were to roll a large number of dice. So I rolled 5 dice. Whilst I can occasionally get a value which is 5 times 6, which is 36, I can't roll a 37. So I can't even though the Gaussian variate has a finite probability of lying out in that highest values, this procedure doesn't allow me to generate those numbers. So there is a cutoff there. But nevertheless, what we've seen here is a consequence of the central limit theorem. The 5 random numbers that I've added together, once I've summed them together and then I do that procedure 1,000 times. Oh, in fact, what I've done here, of course, is I've not used n samples, have I? So let's put that there, n samples. If I run that calculation a large number of times, then you can see that on average I obtain some variate, some probability density for that variate, which is Gaussian distributed. Now, what we haven't done so far is to scale this distribution so that it does something useful for us that we can then scale for our own purposes later. And it would make sense, wouldn't it, to scale this variate so that it has a 0 mean and a unit variance. So how would we do that? Well, let's put another variable here, which is m. So m is the number of numbers I'm adding together, number of uniform variates that I'm adding together to make my Gaussian variate. So to begin with, we'll just replace it. We'll make m equals 5. Put that there. So the mean value is obviously 2.5. So in order to make the mean value 0, I need to subtract m divided by 2. And I'll leave it as an exercise for you to prove for yourself later that if you want to make the correct variance, I want to scale this Gaussian variate so it has a standard deviation of 1, a variance of 1, I need to divide it by the square root of m divided by 12. So I'll save that and run it. Does it look right? And there it is. So by what I've done here is I've taken 5 random numbers, I've added them together, and I've appropriately scaled the mean and the standard deviation so that the resulting Gaussian variate, remember the single Gaussian variate is obtained from 5 uniform variates, this has a standard deviation of 1, and that's it. So you can see that it's computationally complex because I have to roll the dice, as it were. I have to generate 5 random numbers for every single Gaussian variate. So it does take a little bit of time to do this calculation. And I also have to do this scaling of each and every variate, which is computationally expensive as well. And with 5, calls of the random number generator, I still can't generate numbers out in the wing. Actually, the way that which most of these implementations is done is to select 12 as this as the number of uniform variates that I add together. When I do that, you can see that I can generate numbers further out in the wings. If I increase the number of samples to say 10,000, you'll see that occasionally I will generate numbers which are out in the wings. You might be able to see that there are just a few being generated out there. And this is now looking pretty Gaussian, and indeed it is. Now, if I choose m equals 12, there is now a simplification that I can use. I no longer need to divide by m over 12 here. So I can just dispense with that part of the calculation, which, remember, I'm doing that for each and every one of the 10,000 variates. So I'm saving quite a lot of calculations when I dispense with that part there. Also, of course, I know that m over 2 is equal to 6 in this case, so I can replace my calculation with the following expression. So I take 12 random numbers and I add them together and I subtract 6, and I have a Gaussian variate which has a 0 mean and a standard deviation of 1. And of course this Gaussian variate I can now then scale for my own purposes. Say if I want to represent the pattern of spots of light, these might be modelling individual photons falling on a surface, and I wish to have them have a particular sigma, which, say, I don't know, it might be 4 millimeters, for example, and it falls on a screen with a mean value of 10 millimeters. I simply add 10 millimeters to this and multiply the sigma by 4. So I can now use this procedure here as a way of generating a Gaussian variate, and I can generate a single one using this expression. So in later videos we'll show other ways of achieving the same outcome, which is a Gaussian variate. This is not the only way, but this way is used quite commonly.